Okay, so now work and a general variable force. This is not all that bad compared to some of the other things, but it does involve a decent amount of calculus, and specifically calculus with integration. So, in general, just write the equation down and then we'll start working on it from there. We know that work, okay, when it's a regular force, we say work, actually a constant force, I shouldn't say a regular force. It's F dot X. Okay? Now, if we were going to look at that in terms of, let's just say that we had a graph of force versus position. This graph would look something like that. Okay? Because we're dealing with, this would be x0, I'll call this spot x final. And if I wanted to figure out the work, okay, it's force times this, assuming that we're dealing with the direction of motion. This is really saying the force in the direction of motion times the distance. So this F would be the force in the direction of motion. If I wanted to get the work, it would be force times X, which happens to be the area of that rectangle. Essentially, it's the area under this line. Now, when we did a spring, okay, we said that work, and I went through this proof on the last one, work dealing with the spring was equal to 1/2 kx squared. We have x0, x final. Okay, this was the force. This is x. So this is remember, force was equal to kx. Neglecting the negatives at this point for simplicity's sake. So this is kx right here. So if I want to do this, that 1/2 kx squared, well, that's the area here. Okay, and that little triangle. That's pretty straightforward. Okay, this is a force that changes linearly. Well, now, let's say I have a force that goes like this. Let's just say, for argument's sake, my force starts out constant, it drops down, and then it goes constant again. So the x0, here's my x final. Okay. Let's say I wanted to know how much that changed the kinetic energy. Because if that's ultimately why I want to find work. Work by itself is not terribly useful. What you want to do is figure out how much the kinetic energy has changed. Well, if I wanted to do that, notice that the area was equal to the area of the force versus position graph was work when we're dealing with a constant force. Okay, when we have a linear changing force, it's still the case. Okay, that we take the area under the force versus position graph. The area under here, that is the work that's done, which will equal the change in kinetic energy, as long as we're talking about network. Even if it's not a simple function like this, the area under this curve, a series of straight lines, that area will equal the work done on whatever mass we're doing. Now, mathematicians over the past 450 years or so have developed shortcuts for figuring out that area. That area is the basis for integral calculus. Okay? It doesn't have to be force and position, but when you're trying to find the area under a curve, that's what integral calculus is all about. Essentially, calculus is two things: finding a slope and finding an area. Slope, you're taking differential calculus. Integral, you're doing finding areas. Everything else is just offshoots of that. So now, let's say I have a function that looks like this. I have my force here, x is here, sort of a little bit, see it better. And I've got, let's say that my force is equal to x squared. Well now, that equation just doesn't work anymore. Okay, I've got a graph that looks something like that. Here's my, well, x0 is 0 in this case. Here's my x1. You're like, oh, when would I ever see this? Okay, honestly, there are springs that act as x squared. There are any number of things that could act as a force of x squared. So now, what we want to do, the area here, that area of this force versus position graph, this area here is the work that's done. Now, we got to figure out how we can do this. How we can find the area under a curve like this. It's actually not that complicated for simple functions like this. Okay? I probably should call this, I'll call it ax squared. Well, let me just redraw it here. We want to find the whole area. So what we're going to do is we're going to look at little rectangles here. And we take the area of these rectangles. And we can find the area of rectangles pretty easily. Now the problem here, I think you can see, is that I overshoot. If I did this non-infinitesimally, okay, I can find the area of all those rectangles. My problem is that right here, this area right here, I've got little extra areas here. Well, let's say I could really shrink that down. Okay, I could shrink that area down so that it was so small so that the width of this dropped that, so right here, the width of, say, this rectangle right here. If I could shrink that down so small that whatever area I overshot really was inconsequential. Okay? That's what calculus does. You're going to take the limit as your delta x function squishes down to 0. Okay? Now, I'm not going to go through a proof of calculus or anything else like that. Okay? We will talk about in class with those of you who are in Calc AB or Fun Calc, how we can take it in. Okay? But understand, what we're trying to do is find an area. Okay? What we do, okay, this is a dx right here. Okay? We're going to sum all these little rectangles. Because remember, it's dx because it's really skinny. Infinitesimally skinny, I should say. Okay. So if I want to get this area, it's going to be the force that I'm dealing with in this interval. So the work here is the force that's done at this location times this width, and I'm going to sum all of these up. Okay, well, let me just do it the way that you're familiar with. Greek letter sigma. Okay, we're taking a summation of all these little rectangles. Well, when I make this infinitesimally small, instead of a summation where there's a discrete number that we look at, we get what's called an integral. Okay? So this is just an infinite sum as opposed to, or summing in an infinite number of little slices as opposed to a discrete number of little slices. Okay? We're going to understand on Tuesday how to do integration. Okay? Essentially, you're just going to go backwards from differentiation. Okay? It's just going to be going backwards. That's all it is. So now, I is for my initial state, F is for my final state. Okay? Now, if I include this as a vector, which I should, because I have to take that into account when I'm doing this, the final way that I'm going to write this, and this is true regardless of the situation. Net work, work by a particular force is equal to initial state, final state, of force as a vector, function of x, dotted with dx, where x is still a position function. Okay, I'm just looking at a small part of that position function. Okay, so this is our equation that we're going to deal with. Okay. Now, let's see, two-dimensional analysis, not worried about that. All right, now worried about a proof. There is a nifty little proof that you can do to understand. So let's take a look at our original example here. Let's just say that my work here is equal to, let's do a specific number. Force is equal to 200 x squared. Okay. I'm going to say that the mass in this case is equal to 50 kilograms. Let's say that the initial velocity is equal to 6 meters per second. I'm going to say that my initial position is equal to 10 meters. And my final position will equal 20 meters. Just to try to introduce a lot of this. So really I want to be looking at it from here. I'd be looking at it, say, from here as 10 meters and making x finally equaling 20 meters. Okay, I don't want to be looking at this section of the graph. Now, those of you in Calc 2 probably can do this without too much effort. And you might ask, well, what about the whole dot product thing? That is very true, okay? But unless it says otherwise, we're going to assume that the force is in the direction of motion. And we're not going to make it any more complicated than we have to, especially on a first problem. Okay? So we're just going to look at it like this. So now work will equal the integral. Okay, our initial position is 10 meters. Our final position is 20 meters. Our force is 200 x squared, that's f of x. And our dx is just dx. Okay. Now, for those of you in AB Calc who haven't done integrals yet, or Fun Calc, haven't done integrals yet, try to imagine what function would give you a derivative of 200x squared. So in other words, we're going to go backwards logic. We're going to try to go back to it. First of all, the derivative of what will give you an x squared? The derivative of what gives you an x squared? You should be thinking x cubed. Okay. Something x cubed gives me something x squared as a derivative. So let's take a look. Okay. If I try to work this backwards, all right, I'm going to take this right here, okay, raise it to one higher power, so that would be 3. So I'm going to start off with the 200x squared. I'm going to raise it to one higher power, so I say, all right, the 200x squared cubed. Now what did I do when I took a derivative? Okay, I multiplied this by whatever's out front here. So if I'm going backwards, I'm going to divide. So I get 200 over 3 x cubed. Let's check. If I took the derivative of this, just kind of do this off to the side here. If I took the derivative of 200 over 3 x cubed, well, I multiply 200 over 3 by the exponent, so that's 3. X to the 1 lower power, x squared. 3's go, 200x squared, 200x squared. We're good. Now, I have to do that between 10 and 20. I think that 6 in the 6 meters per second is going to be utterly meaningless, but still oh my gosh, yes, it's going to be. Might have to crank up the mass here a little bit. Let's make that, instead of 50 kilograms, let's crank that up to 5,000 kilograms. So now, this will be 1,000, so I have 200,000. Okay, what you do, for those of you in Calc 1 now, okay, we're going to plug in start and ending locations. Okay, I'll go over it in more detail on Tuesday. But I'm going to take my ending location and I subtract my initial location. So I take this function, I plug in the 20, that's the end. I subtract from it the 10, which is at the end. So I have 200 over 3 times 1,000, excuse me, 4,000. And I subtract 200 over 3 times 1,000. Okay, compare like terms, that's 3,000, 600,000, 1,000, 1,000. So the work that I do is equal to 100,000, and I know I've dropped units, 100,000 joules. $50 kilograms would have been a lot of work. 5,000, and now we're dealing with something. So now, I should have said actually what we're looking for here. V final ultimately is what we're looking for. So now, work is equal to a change in kinetic energy. Now the 6 meters per second is a lot more reasonable. So now, I have work is equal to 1/2. I have 1/2 mv final squared minus 1/2 mv initial squared. So, you guys like to plug in on it, whatever. Joules is equal to 1/2 mass, which is 5,000 kilograms. V final squared. I hate plugging in early. 1/2 5,000 kilograms times 6 meters per second squared. I hope I didn't run off the edge. I don't think I did. So now, 100,000 joules. 2,500 kilograms times v final squared. We want to make sure that our answer makes sense. So that's 3618 times 5, which would be 90,000. Okay. 3618 5, 90,000. Okay. So now I get v final squared is equal to 190,000 joules over 2,500 kilograms. So that's 4 would be 10,000. So I get a v final squared of 76. So that gives me an answer of 8.7. So my final velocity is equal to 8.7 meters per second. Okay. All right, one final thing that I want to talk about before we have before we move on here and end up. I want to talk about power. Okay. Power is equal to the work that you do divided by the time. Okay. If that's all it is, then it's simple, and all you have to do is just calculate the work divided by the time. Okay. But a lot of times you're dealing with force, you're dealing with velocity, you're dealing with position. So, however you have to get work, you get work. But there's another way we can rewrite this. It's the only reason why I'm really going over it. Otherwise, you just take whatever work you have and divide by time. Or you can look at it as change in kinetic energy divided by time. Okay? Those are the key things that you'd be looking for. However, power is equal to work is force divided with x divided by time. And really, we're looking at changing states here. So, however that works, this is x divided by time. In fact, so if this is my distance divided by time, that's velocity. Power is equal to force divided with velocity. This could be something that you could definitely see. I would not be surprised to see something like that on the AP test. Okay. Also, okay, we could say differential. We're looking at it. Instantaneous change here. Okay, it's the dw dt if you're looking for the instantaneous power. But that is. Okay, that's just one other part of the power. That's the only other thing that we would see. Really, everything else we're going to work on with problems. All right, I'm going to make one final lecture, and that will be the AP. That will be for the calculus lecture. Okay. All right, so I will see you in class on Tuesday.